Good morning. Last session we introduced the statistical hypothesis test number 4, which is this two independent groups design. And we have this test, this hypothesis test called the two independent sample t-test, where our t-statistic again is this mean difference divided by the standard error of the difference. And if we remember, we're working in this sampling distribution of differences between means. And again, every little infinite amount of data points on this sampling distribution is a mean difference expressed as, x bar sub 1 minus x bar sub 2. We left off last time with a little exercise. An educational researcher working in the area of decision making asked 12 sixth graders to solve as many problems as they could in 45 minutes. Half the children were told that this was a test of innate problem-solving ability, and the other half were told that this was just a time-filling task. The dependent variable is the number of problems solved. Compute and interpret. So we have two independent groups. One of the groups was told that this is just a test of innate problem-solving ability. The other group was told that this is a time-filling task, and you immediately see that there's a difference here. In fact, the group that was told that this is a test of innate problem-solving ability scored substantially, solved substantially more problems than, the kids that were told that this is just a time-filling task. Last time we reintroduced the concept of statistical power, and we said that this is the reason why we either reject or accept the null hypothesis. And we remember those four things: mean difference, sample size, within group variability, and alpha. With this particular situation, we have a substantial mean difference here. We don't have a whole lot of power in terms of sample size, and we have a lot of within group variability with a pretty vanilla alpha of 0.05. Now the question becomes, is there going to be enough of a mean difference to counterbalance what's going on in this denominator, right? To produce a t-statistic that is large enough to be deemed statistically significant. The decision whether to reject or accept is actually based on those four things: mean difference, sample size, within group variability, and alpha. On the exam coming up, you'll have a computational question that involves this two independent sample t-test. One of the questions will be write the null and the alternative. So we have a null hypothesis which states that the means are equal in the population. The alternative is the opposite. The means are not equal. This problem calls for an 0.5 alpha. Degrees of freedom is 6 plus 6 is 12 minus 2 is 10. And we know that before we run any statistical test, p equals alpha. So we have 10 degrees of freedom, 0.5 alpha. We have to divide alpha by 2 to get the area in the one tail. And we go across the top to 0.25, down the side to 10, and there's a number there. What is that number?
10.228.
Yeah, so it would be positive or negative 2.228. If t exceeds this, we have enough evidence to reject the null. And again, this is telling us that at 10 degrees of freedom, about 95% of the area under this sampling distribution of differences between means falls with within these two critical values, 2.228, positive or negative. We can actually compute this t-test very simply. T is the mean difference divided by the standard error of the difference. The variance of the first group, 69.47, over the n of 6, plus the variance of the second group, 123.81, divided by the n of 6. And if we, work this through very simply, t ends up being negative 2.82. And we have a decision to make, again, using the rule. On the exam, there will be lots of opportunities to make this decision. So you need to know your rule, really well, just like last time. We compare the calculated statistic to the critical value. We see it exceeds it in the negative direction. Therefore, our decision would be to reject the null. Reject the null. Let's answer a research question. Okay? Class, did it take, did the kids who were told that this was a test of innate problem-solving ability solve significantly more problems than the kids that were told that this is just a time-filling task? Yeah, apparently so. What happened to our p region? Well, it got smaller. We know if p is less than alpha, we reject the null. And again, we know this because before we actually ran the t-test, the needles were right here and here at the critical values. But t turned into negative 2.82. This needle stayed the same. Therefore, this area remained at 2.5%. But this needle shifted from here over to negative 2.82 and actually reduced the size of that particular area of p, therefore having a total effect of making p less than 5% of the area under the sampling distribution of differences between means. So again, despite the fact that we didn't have a whole lot of power here or here, we still had enough of a mean difference to counterbalance that and produce a t result that was statistically significant. In other words, this numerator was large enough to counterbalance that denominator and make t large enough to be deemed statistically significant. And again, we know that we have a rare event here. Rare events are significant events. Don't happen every day. What is the type 1 error rate and what does it mean? Well, let's look at this. We know that there's about a 5% chance that my decision to reject this null was not a correct one, so I rejected with, some pretty high certainty. If we were to replicate this situation 100 more times based on this information, we would correctly reject the null 95 times, incorrectly reject the null 5 times. And what is the probability that the observed differences were due to chance? Pretty small, like maybe 5%. Pretty high likelihood that these observed differences are real and exist in the population. So again, we have just another situation where we have two independent groups looking for significant mean difference between those two. Okay, I'd like to talk about very quickly some assumptions. The two independent sample t-test comes with a set of assumptions. We're going to call this assumptions for the two independent sample t-test. The two independent sample t-test comes with a set of assumptions. Our first assumption we call the randomness assumption. The randomness assumption. It's assumed that our two independent samples, randomization was actually utilized in the selection of these two independent samples. Now we know that if randomization was utilized, if we had random selection and perhaps assignment, we can do what? It enables us to do what? It enables us to generalize from sample to population. Yeah. So it's assumed that we've utilized randomization. Our second assumption for the two independent sample t-test we call the normality assumption. Normality. Now different textbooks will actually define this different ways. One textbook will say, the frequency distributions of both our samples are normally distributed. Open up another stat textbook, it'll say the population distributions for our two samples are normally distributed. And even other textbooks will say the sampling distribution is normally distributed, which we already know. I mean, that's a mathematical law. Okay, so, whatever. The frequency distributions of both our samples are normally distributed. Let's just stick with that. It's assumed that that is the case. Our third assumption for the two independent sample t-test is a new word, and it's called homoscedasticity. Homoscedasticity. Big word. New word. Homoscedasticity. It means homogeneity of variance. Homogeneity of variance. It's assumed in this two independent sample t-test that the variances of both our samples are actually equal. They're very equal to each other or pretty close to each other. So you could consider it, equality of variance, so to speak. Our fourth assumption we call independent observations. Independent observations, also called independent ends. Independent observations. It's assumed that our two groups are independent of each other. We have group 1 and group 2, and there's no real relationship between the two. Now back in the correlated t-test, or back in that dependent sample t-test, our post-test was dependent on the pre-test. So we had a dependence relationship. In this situation, in number 4, we have an independence relationship. So we have our 4 assumptions. Please do not confuse these with the 4 elements of statistical power. On the exam, I might ask you, what the 4 elements of power are. Don't write this. The reason I say that is because sometimes students do, and they confuse them, because they each have 4 things. Don't write this. Okay. Now, up to this point, we've actually covered 4 statistical hypothesis tests. So we're really moving right along. And I really believe in my heart of hearts here that I would be doing you a big disservice as a teacher if I just didn't talk about one more hypothesis test. Let's talk about just one more hypothesis test. This will only last about 3 minutes, okay? Do you guys remember that Pearson R? Yeah, you remember Pearson R. Well, guess what? We can do hypothesis testing with the Pearson R. You see it all over the place. Hypothesis testing with the Pearson R. You remember Pearson R back from descriptive statistics. Well, guess what? It's also an inferential statistic. And if you guys remember, we have variable x, variable y, and we're looking for a relationship between variable x and y. And we have our data. And we computed quite a few Pearson R's in the first section of our class. And let's just say we have a data set and we computed Pearson R, and R was equal to, I don't know, like negative 0.78. I think that was actually one of our answers back in the day. Well, we can do hypothesis testing. What does that mean? Oh, we're testing a null hypothesis. In this case, we know that hypothesis testing is all about population parameters. So we know that the corresponding population parameter for the sample statistic R would be rho, right? So the null hypothesis is rho equals 0. And we know this implies no relationship. No relationship in the population. No relationship in the population. Our alternative hypothesis, two-tailed of course, rho is not equal to 0. There is a relationship. We can set alpha at 0.05. We can run a two-tailed test. Why would the researcher choose a two-tailed test? Well, actually before the data was gathered, they didn't know whether the correlation would be positive or negative. They picked a two-tailed test just to be safe. We know that before we run any statistical test, our p equals alpha. Degrees of freedom in this case is n minus 2. We can find an R critical value. Now in some statistical textbooks, they have R critical values in the back of the book. In this one, they don't. But you see another example of hypothesis testing. Same drill, different question, right? Is there a significant relationship between x and y? That's the question. Let's suppose we were able to find, a critical value at a given nominal alpha and degrees of freedom. And let's say this critical value was positive or negative 0.32. We've computed a Pearson R of negative 0.78. What's the next step? Oh, we have a decision to make, don't we? Yeah. Use that rule. We compare the calculated statistic to the critical value. We see it exceeds it in the negative direction. Therefore, our decision in this case would be to do what? Yeah, reject the null. Same drill. And conclude that we have a significant relationship between x and y in the population. So in the scientific literature, you see a lot of this. And so again, the notation, would look like this. R equals negative 0.78, semicolon, p is less than alpha, in this case 0.05. So in scientific articles, whenever you see this notation, you automatically know that a null hypothesis is rejected. P is less than 0.05, P is less than 0.01, P is less than 0.001, a null hypothesis has been rejected. P is greater than 0.05, greater than 0.01, a null hypothesis has been accepted. So, again, as college students, sitting here in any college class, when a professor is up here singing and dancing and putting things on the board and explaining things and everything and being real repetitious and such, What are they actually doing?
They're preparing you for the test.
They're preparing you for the test. The answers are right here. It's your job to anticipate test questions. What's this guy going to ask me? Well, here you go. Test questions. Here we go. Let's see. I could write a question. See, you should be writing your own test questions. You should be quizzing yourself. Here we go. I could write a question. The null for Pearson R is what? And then A, B, C, D. Well, you know what? You know the null has the equal sign. So you look in those answer selections for the one with the equal sign, you know? And if I'm writing the test, there's got to be one right answer, right? So I'm probably just going to include one equal sign. Excuse me. Okay. I might give a rejection scenario. I might give you an R calculated and give you some little situation and then tell you what the critical value is. And I want you to make the decision using the rule. And I want you to use or I might just give you a p-value like I did on exam 2. And you make the decision. So, is this p less than alpha? If it is, I got to reject. If this p is greater than alpha, I'm going to accept. Now, the reason I'm bringing this up is that on exam 2, a lot of you missed questions on those decisions. You know, I'd really drilled you on those decisions. So you need to be prepared, you know, to answer those questions. Okay. The Tuesday after we get back from spring break, we're going to have exam 3. And coincidentally, this morning when I was sitting there making my French roast, sitting there and percolator was gurgling, and I just so happened to have a copy of the test in front of me. I looked at all the questions. Let's talk about that a little bit. Let's have a little review. This exam 3 will have 73 questions, and there's really never an issue with finishing on time because a lot of the questions will be easy, where you just, it's obvious, and you circle the right answer. About 15% of this exam will be computational. You're going to compute a correlated T and a 2 independent sample T. And there might be like 5 questions on each. You know, write the null and the alternative. What's the significance level? Find the critical value. What's degrees of freedom? You know, all that. Just real simple stuff. Compute the T, make the decision. Maybe a little bit on interpretation or something like that, just like on the last test. But those 2 computation problems will only be about 15% of the questions. The other 85% of the questions will be conceptual in nature. Why? Because as you see, statistics is a language. I mean, there's a lot of terminology with statistics. There's a lot of conceptual stuff that you have to understand, and it's really a sort of a scientific, kind of a science discipline. So this is going to be an exam on inferential statistics with a focus on hypothesis testing, like we've been doing, with a real focus on hypothesis test number 3 and 4. Okay? But there's going to be questions, there's going to be basic questions from that very first lecture. And you have the notes. It would be a good idea to have those first lecture notes with all this conceptual stuff, you know, and know this stuff like crazy, you know, because, you know, for instance, I'm going to ask you just maybe a simple question on what inferential statistics is. You know, taking sample information and attempting to make sense out of it in terms of how it equates to the population. Now, if you remember on the last exam, there was a couple questions, maybe a few questions on point estimation. So, you know, it's up to you to be able to identify when, you know, we have a situation where we're taking some sample measurement And we're automatically concluding that it's the corresponding population parameter. So it's up to you to, read into that scenario and be able to know what's going on. And no, it's not the wording. It's not the wording. It's your level of understanding combined with reading comprehension. Okay, it's not the wording of the question. We're in college. We're all pretty bright. So we can read a question and ascertain what is going on. If you see a situation where we have some sample measurement, and it says sample, in a sample of blah, 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 and then it'll say for all the blah, blah, the all, that's population, all right? So if you see a situation like, it's point estimation, and you ought to be able to identify that. I'm going to have a number of questions on central limit theorem and sampling distributions. And by the way, I emailed you a copy of key terms. Who printed that out? It would be a good idea to print that out. It doesn't do you any good to have it sitting in your inbox. It's just in your inbox with a million other things, okay? Central limit theorem and sampling distributions. Know the tenets of the central limit theorem. Normally distributed, infinite amount of sample means, right, or mean differences. The mean of the means equals the population mean. The dispersion of those means or mean differences around the midpoint is the standard error of the mean or mean difference. So know those three elements of the central limit theorem, and know that what that central limit theorem is describing is the sampling distribution. And a sampling distribution is just simply the version of a frequency distribution that we use in inferential statistics to describe what would happen if we were to take an infinite amount of randomly selected samples of a fixed n and plot all those means, or mean differences now, right? They would be normally distributed. Mean of the means equals the population mean. Dispersion of all those means around the population mean is the standard error of the mean or mean difference. So know what a sampling distribution is, and so given that, we spent a little bit of time on interval estimation. Now, you won't compute any confidence intervals, and we have not been computing confidence intervals because it's pretty secondary in the grand scheme of inferential statistics. But I am going to expect you to know what a confidence interval is. It's a situation where we estimate a range. Look for that keyword range. That's the tip-off. The range of potential sample statistics, it's usually the mean. If we're given a set of sample information, if we were to replicate this an infinite amount of times, what would the range of those infinite amount of means be? And we can actually estimate that range using this procedure called a confidence interval. And we can predict, so to speak, with like 95% confidence or 99% confidence that the range of those potential means will be within a certain interval. End of story. And as you guys have seen, we've spent the majority of our time on hypothesis testing. Why? Because it's major. Hypothesis tests are used to answer research questions. So each hypothesis test that we've studied is designed to fit a specific research question. You will have very simple basic questions on the basics. For instance, what is hypothesis testing? Or what is a p-region? You can expect a question on the one-tailed hypothesis. What is a one-tailed hypothesis? And you should probably remember that it's a directional hypothesis, right? What is a two-tailed hypothesis? And you should probably remember that that's the non-directional hypothesis. Know what a null hypothesis is. Know what an alternative hypothesis is. And yeah, There's going to be some questions on, the rule, which is the critical value approach in the book, and the p-value approach. So you're going to have to know, when to reject the null, when to accept the null. We've only done that rule a cajillion times in our examples. So I'm assuming that that stuff's automatic now. And, before we run any statistical test, p and alpha are the same thing. And questions on type 1 and type 2 error. Yeah. Just like we had on last test. You're going to be expected to know what those are. What is a type 1 error? It's rejecting a true null. What's a type 2 error? It's failing to reject a false null. And we know that when we have a significant result, small chance I may have made a type 1 error, that's the alpha that we select. Likelihood of a type 2 error is irrelevant. When we have a non-significant result, small chance I may have made a type 2 error, alpha is irrelevant. Also remember the symbols, alpha and beta. We talked about statistical power, the 4 elements of power. Know the symbol for power, 1 minus beta. Know what power is, okay? The likelihood of correctly rejecting a false null. It's the likelihood of finding significance, and it's a function of 4 things. Mean difference, sample size, within group variability, and alpha. And it's these 4 things working in interaction that produces a statistic that is either statistically significant or non-significant. You're going to compute a correlated t and a 2 independent sample t, like I said. But you know what? There's going to be some questions on the z-test and the 1 sample t-test. So in fact, I'm going to give you, you need to anticipate questions. I'm going to give you a scenario. You tell me what the appropriate statistical test is. Like for instance, if I were to give you a mu and then give you an s, mu is known, but sigma is unknown, so s is given, we would know that it's the 1 sample t-test as the appropriate test. If I give you a mu of 63 and a sigma of 4, right? Sigma is known, mu is known, that would be a z-test. So you're going to have to know when to use a z-test, when to use a 1 sample t. I might give you a situation, a before and after situation with the treatment in the middle. You know that that's the correlated t. But that correlated t has 2 other names, doesn't it? Yeah, paired t-test, dependent sample t-test. Do not forget that there's 3 names for that. I'm telling you right now. If I give you a situation where we're looking for significant gender difference, gender, let's see, this is not in the wording. How many genders are there? 2, men and women. We have 2 independent groups. What's the appropriate test? The 2 independent sample t-test. So you're going to have the ability to know when to use a particular test. Now, all statistics students, intro stat students have to do this. This is just, just the way it is.